All right, recording is rolling. It is Thursday, March 14th, the last day of the week. You guys have tomorrow off. So, you guys have, remember, last few days we've been looking at these algebra-based questions for relativity. Printed on the same paper on the opposite side is the puzzle we're going to focus on today. This is what kickstarted this section. You guys remember back in 1849, this guy Armand Fizeau trying to figure out what is the speed of light and figured out how to do figure out an accurate answer with this method. So I'm going to have you guys basically solve this problem, but in reverse. I'll walk you guys over that too. Right? So you guys have this out, ready to go. Look at that. If you finish by the end of class today, then you can turn this in. I'll put it on next quarter. So I'll put this on fourth quarter. Right? If you struggle with this a lot or want to go home and check your answers and make sure they're right first, then it's okay if you want to turn this in Monday. That's right too. Right? All right. So my AP classes voted to have a class concert on Thursday coming up here, so let's go do that. If you play an instrument or want to play something for the class, then you can do that on Thursday. All right, before we look at that puzzle, I'm gonna show you guys a demo for general relativity. Right? So you guys remember there's like two halves of this relativity story. Special relativity has to do with space, time, and motion. The faster you go through space, the slower you go through time, kind of thing, right? The twin paradox, the whole deal, right? And then general relativity also incorporates gravitation. So if you're next to a huge gravity field, that will also slow down time, right? A lot of times this visual is shown to represent like space-time for general relativity. The idea being like this blue fabric, what if that represented like four-dimensional space-time? So we're going to take like the three spatial dimensions and put this on like a 2D plane. And then, this weight in the center maybe represents like the sun, it could be something like that, right? And then, so you see like a 3D representation of 4D spacetime, right? So that's kind of what this represents, right? I think like little marbles out there or something, right? Maybe this could represent like asteroids or planets or something, right? Right now, I've got it muted, but what he's explaining is why is it that all the planets go around the sun at the same direction, right? Why aren't there planets that go opposite directions? Well, maybe when our own solar system was forming, say about 4.5 billion years ago, when it was, he's making the case. Well, maybe everything was scattered all different directions, all going around, right? But what you'll notice is that after time, after so many collisions, there tends to be like one direction that dominates, right? And everything else like falls into the sun or something, right? So you got that. So that could be like a comet going something like that, right? Right. It's somewhere in here. There it is. Right. He's showing like right. I don't think it's his best take, but it's got somewhere he's showing like the moon going around the Earth, right? So is that coming up pretty soon? I think he does a retake here. How about these video spikes? Probably get some good takes. Yeah, all right. So again, to contrast Einstein's version of gravity with Newton's version of gravity, right? Newton was thinking, well, maybe gravity acts as some attractive force, right? Inverse square law with distance, right? And it could hold the moon in orbit around the Earth that way. But Einstein says, well, actually, the moon is just following a straight line path through curved space-time. Ooh, okay, there's like a double star system, something crazy going on. Right. So everything only ever moves in straight lines, but space-time is curved by masses. All right, so there you go. There's a representation of general relativity. All right. All right, so let's look at this puzzle. This puzzle here. All right, actually, I got my own version. All right. So, like usual, there's a bunch of different versions of this going around. So my numbers are going to be a little bit different from your numbers, right? But we all get the same premise, the same question. Right? So here's the setup. 1849 accurately measured the speed of light, or I should say calculated speed of light, right? By spinning a toothed wheel. A beam of light would pass through one gap. If the wheel was spinning just fast enough, then after being reflected back, the beam would hit a tooth adjacent to the gap. So the reflection of light would not be visible behind the wheel. Yeah, I have a poster for that. Let me find my poster for that. Gotta dig this up. Aha, this one right here. I'm thinking of, right? So maybe there's a little bit better picture, right? So if the wheel's not spinning, then light reflects off this mirror, which is maybe several kilometers in the background. You come back and you can see it. But if it's spinning, just so that it turns this little angle theta. Right? Then during the time it takes the light to go to the mirror and back, right? Well, now it's hitting a tooth. Now this observer on the side of the wheel can no longer see the reflection. Okay, so got that geometry set up. Right? Right, this poster, do you guys see it's hanging right there, above the door over there on that wall? Or I think I gave you guys a thumbnail version of this too, so you guys have that. Maybe that could be really helpful for this particular puzzle. Okay. All right. All right. So he was trying to figure out what is the speed of light based on some known values. I gave you some known values here. Okay. Now, since you guys know what the speed of light is, I want to have you guys solve this problem exactly backwards. So it's just as difficult, but you're solving the backwards version. Okay. I'm telling you what the speed of light is. Right? 3 times 10 to the 8 meters per second, or more precisely, 299792458 meters per second. That is the definition of the speed of light, right? And it's, again, observed to be that speed anywhere, as long as it's going through a vacuum, regardless of your frame of reference, right? Just to hammer this point, even if you're traveling in a spaceship at half the speed of light and there's a light beam that goes by, you will still measure this as the speed of light, right? Special relativity, right? Right. I'll give you some other numbers too. Let's say the distance from this wheel to this mirror is so far, right? Now my paper says 3 kilometers, 3 kilometers, right? Do you guys think, having been in this class for a few months now, do you guys think before you start plugging and chugging with numbers like this, you probably have to convert kilometers to what first? Meters, right? And guys, how many meters are in 1 kilometer? Kilo is a factor of a, right? Oh, I told you the diameter of the wheel, in centimeters. How many centimeters in a meter? I told you the number of teeth on the wheel. So my paper has printed 29, which happens to match the picture. I think there's like 29 on that particular wheel, but you might have a different number of teeth on your wheel, right? Something like that, and a different distance to the mirror and motor, so different values, right? But we all have the same speed of light. And my main question here is, how fast did he have to spin the wheel, given these input numbers, so that everything would align and therefore he could calculate what the speed of light was? Okay? So how fast is that wheel spinning to make this whole thing work? Okay. I'll give you guys some hints down here. I got some hints. One method of solving uses, in physics, a lot of times there's multiple ways to solve these things. Okay? Uses only 3 of the 4 provided values. I gave you these 4 values. Obviously, the speed of light matters, okay? But these other values, actually, one of them is completely irrelevant. I wonder which value is completely irrelevant. Is it the distance to the mirror? Is it the diameter of the wheel? Is it the number of teeth on the wheel? Right? You don't actually need all those numbers, right? But depending on how you solve this too, you might possibly use all those numbers. Maybe one of them is like a middle step, right? But there's a way that something cancels out, maybe, or is irrelevant anyway, right? I gave you guys this hint. I'm gonna write this bigger for the camera also. Is that linear distance equals angular distance times radial size? Right? You guys remember that from a few weeks back? Okay. Right, so I think I got a poster for this too. I remind you guys the poster, the version of this. Oh, actually, I think this one's hanging up in my room. It is. It's up by the door here. You guys remember this one? Right? Because my AP students were reviewing angular, like rotational motion right now, so they need this. Right? So what this is like, if you have a turntable turning. Oh, and you guys have a cogwheel that's turning, right? Right. If I want to say like how far has it turned in like degrees or radians that you could measure with a protractor? Like how far is something turned like protractor wise? Okay? I would say, like, how far has a point moved out on the edge in terms of like meters, like centimeters or meters? All I have to do is take how far it's rotated in radians and multiply by the radius. That'll tell me how far the point is moved, as a linear value. Okay, you guys remember that? Now it is key that theta has to be in a radians. If you put degrees, then you get nonsensical answers. Okay, you're only allowed to use angles and degrees if it's inside a sine, a cosine, or a tangent. Right? If you're directly multiplying an angle, right? We're just reminding you guys from a few months ago. You guys did this right? Back in December. You guys did this. Okay? If you're ever directly multiplying an angle, it has to be in radians. Okay, so you guys got that as a hint. And the last hint I gave you is it's actually really similar to that. It says linear speed is equal to angular speed times radius, right? So angular speed, you guys might remember, is in radians per second. Radius could be in, so like meters. That could give you velocity in meters per second. It was like meters per radius. How about that? Okay. Right. So you guys remember that too? All right. Now maybe you could use the poster I gave you to kind of work it backwards, get to the answer. I gave you guys a bunch of guiding questions on the right of the page, right? So if you follow these questions one by one, and you just like answer each question, it sort of like leads them to the next variable. And then you can put this together at the end and it leads you straight back to this, right? Also, you might notice halfway down, it says, hint, one method of solving this question utilizes only these above 3 boxes, right? So after you're solving, suppose you answer the first question first, and the second question, and the third question. By the time you get to the third question, you actually are one step away from getting the answer. So you could just immediately get the answer from there, right? Or you could continue on this route and say like, what is this like in terms of linear values? And then answer these other 3, and then answer the question from a different point of view down here, but you'll get the same answer, right? Now, when you guys turn this in, how am I going to score this? I'm going to score all 7 boxes, right? So are you getting all 7 of these correct? Okay. You guys set? And so I'll give you guys this class to, you can work by yourself, you can work with each other, you can help each other out, that's okay too. See if you can figure out the answers to these 7 questions. And the ultimate question is, how fast does you have to spin the wheel to measure the speed of light? All right, so that'll be a wrap on the recording right there.